Hello everyone. Hello Akshay.
Hi, Bika.
Hi, how are you?
Yeah, we are doing great. So Tavish and Tulsi has joined. So actually we will start with Tavish, and it gonna take probably for 50 to 60 minutes, and after that we will discuss with you Tulsi. So it's up to you whether you want to stay with the whole session, or you may join up at 10,
Um,
like after 1 hour.
yeah, that works for me. I'll join after an hour. If you finish early, you can text me in Slack.
Okay, so you please join at 10, and if
Yes.
we are like continuing then for like 5 or 10 minutes, then you just stay in the meet, and maybe then we will start at 10:05 or 10:10, but join at 10. Okay.
Okay.
Okay. Actually, we should start with Tavish.
Yeah, that was great. Thanks, Pritam. Hi, Tavish. We'll discuss today about the problem statement given to you. It is on different formalisms of quantum mechanics that you have to implement for the application of classification. Hope you have gone through the code and the document shared with you. If not, then after today's session, like after the discussion, you will get to know the task, the detailed overview. Then you can go through the notes, so notes as well and the code as well, and we'll walk you through the code as well. So without any further ado, let me share my screen. Yeah. So we'll begin first with okay. We have this two three documents for it. Okay. Okay. Uh, so um, Yeah, this is our quantum formalism document. So, it would be better if I explain it via slide. That would also be fine. Like these formalisms are all written on slide. Fine. We'll begin from here. In between, we'll switch to slides. In between, we'll switch to writing notepad. Okay, fine. So let me open the slides. The slides are open here. Let me open this notes as well. Okay. Okay. So today's discussion is going to be about quantum formalisms. So we are going to discuss whatever we have provided you the code for, as in a demo code for, as well as in detail code for Everest we have provided, and then you have to implement that for the other formalisms we will discuss here. And then if the time permits, you have to write the report about the remaining quantum formalisms which we have given to you. So that also will come. Have a brief discussion about like what you have to do in that. So first, without any further ado, we'll begin Heisenberg quantum formalism. So what exactly is Heisenberg quantum formalism of quantum mechanics? So how it can be applied for the application of classification data set. So that will be our key point. We don't have to focus on too much theory. We have to focus on the application oriented side. So we'll directly begin with the equation. So we'll directly begin with the steady state equation of Schrodinger as a stationary equation. So this is our stationary equation, which is time independent. So H is equal to E star. So that is nothing but your stationary equation. Here, what Heisenberg formalism basically tells us is that uh, uh, Hamiltonian is basically a Hermitian matrix, which is basically a finite set n cross n matrix, which is a finite set n cross n matrix. So as in what it basically tells us is that this is not a continuous function, it's a discretized version, like which can be expressed into basis states, and if that basis states we have considered is finite, it can be taken as a finite matrix of n cross n. And for the application of classification or any real life application, this will be a finite basis like matrix. So as in the elements will have a finite dimensions, n cross n. So what this n cross n basically is nothing but 2 raised to n cross 2 raised to n. How many number of qubits you are taking, that n is nothing but qubit here, and n is the dimension of the matrix. So this dimensionality transition is clear, hopefully. So this hopefully this is clear. So all the Heisenberg in the Heisenberg quantum mechanics formalism, all the observables what we'll be dealing with, all the operators, all the observables, all will be in the form of finite Hermitian matrices. So hope that point is clear. That is one of the point. And second point is it should satisfy like the criteria of whatever it should satisfy the criteria of let's say uncertainty principle. So it should satisfy that one criteria, but it is not required for your end. So it will be required for the parameterization of classical data set. But let's move on. So this psi what we will be discussing is also a vector here. It's a discretized form of a vector. So what you can do is you can write it in terms of x0, x1. So what are the basis states, right? Basis state as in if you're taking x0 as the basis state, x1 as the basis state. Basis state as in if you consider it as a zero on basis, then you can do what you can do is you can write in terms of this state. So this will be your zero state, and it will have the probability amplitude associated with this. So whatever value you have written here after normalizing, right? So we are talking about the amplitude encoding first. So whatever value will be written here, that will be your probability amplitude, plus whatever value will be written here, that will be a probability amplitude for the next state, then so on up to the final state. Okay, so hope this point is clear. So that is nothing but your discretized version of wave vector. We have been dealing with this, the whatever code was shared with you, that specifically implement for Everett as well as other implementation. This is only the implementation that we have shared with you, as in for amplitude encoding. But what you can try here is you can try remaining kinds of encoding as well for Heisenberg quantum formalism. So hope this formalism is clear. As in, so for the application of classification, whatever computing circuit we have used, that computing circuit is this unitary, first tuple unitary of mapping, and then unitary of segregation or unitary of separation, and then the measurement, or the measurement means measurement is not required in inspired approach. We were directly finding this unitary with the help of target states that we have defined that are analogous to one hot label encoding. So hope this point is clear. So here what we're talking about is this unitary what we're dealing with, right? Heisenberg quantum mechanics formalism is a matrix. That's it, and that's the finite matrix for our classical data set. So that is what we're dealing about, and this is a wave vector. Okay,
So my task would be to
yeah. So like we will be coming to your tasks in the code also it is explained. Now we are just walking you through what exactly is the like document share with you, the explanation of that. So we will be clearer about the problem statement with the concepts. Like we'll go into you can say medium depth of the concepts here. So that will be sufficient for you to tackle the project. So that's the point. Okay, fine. So this is, yeah. Moving on. So second what we'll be discussing is Schrodinger. So Schrodinger wave mechanics formalism, or Schrodinger wave, you can say wave formalism. That wave function is nothing but, so wave function you can say wave function formalism. So in that, what you will be dealing with is the equation remains the same. H psi is equal to U psi. We have been dealing with why a time independent Schrodinger equation, as in why, because whatever classical data set if you observe, that has you can assume that it is inherently assumed that the probability like distribution of the data is taken when there was maximum entropy, as in the free state, there was a maximum entropy as in the free state or the free energy was reached, as in it's a stable configuration. It does not change with respect to time, the probability distribution I'm talking about. So that's why we're not going into the time dependent, we're taking out time independent. So hope this point is clear. Free energy, so fine. So moving on, what exactly is the Schrodinger formalism here, we'll go into details of. So first what you can do is whatever so you're aware about the Schrodinger equation, right? So that h what you'll be having, right, that is a continuous function of the configuration space parameters. So what exactly are the configuration space? They are not real spaces, x1 x2 x3 x4 like that, they are the configuration spaces. So here what they will become, they will become the feature vectors, as in the basic states of the feature vectors. So this x0 x1 x2 so on up to, for our case it is 1024 1023 for our case, as in the vector size will be limited to this case. So this will be nothing but the function of these states. So hope this point is clear, x0 x1 x2 up to x1023. So this function is a continuous function rather than a matrix. It's a continuous function. So that continuous complex function, and it should satisfy what criteria? Continuous complex function, as in the probability amplitudes can be complex here. Okay, so what exactly do I mean by continuous function? We'll get back to. And okay, fine. So this essentially is now what. So you are aware about Hermitian matrices. So how does Hermitian property come into picture here? So it will be derived from your unitary property. So if you, I'll just go over the brief concept. So if you plot whatever data you have, just take a single vector of your data, m niche data set. So you can plot your x0, x1 up to so on 1023, or for simplicity, let's say we just have 63. As in whatever vector you have just a 8 cross 8 image. That 8 cross 8 image you flatten, you're getting the 64 cross 1 vector, and that vector is normalized here. Okay, fine. Now what will be plotting? So these are nothing but the basis states. Basis state as in this state, this 0 0 up to, so how many zeros will be here? As in number of qubits. So number of qubits for 64 are nothing but 6 qubits, so you will have 6 zeros here. As in then this will be 0 0 0 1, like 5 times 0 then 1, like that. So these are the basis states. Now Schrodinger equation, what does it do? It forms a continuous, as in you can say transition from the basis state. So these basis states are not discretized version, they are continuous in continuous form. So it cannot be written first of all in this format. So hope this point is clear. So like what we'll be doing is whatever discretized value we have, right, we'll be plotting in this way. So as in what value of this corresponds to is probability amplitude of x0, right? Probability amplitude of x1, probability amplitude of x2. Those are this value, right? These probability amplitude values which are discretized in Heisenberg formalism should be continuous here. That's the whole point. Okay. So how to make it continuous? Basically, whatever values we have, we can take that as a sample space and we can plot it continuously. As in if let's say values are like this, something values are like this. Specifically for m niche data set, we have plotted it. We can show you some values like this are there. So what you can do is you can form a curve fit here, continuous curve fit here, and what equations come from here, right? That equation of curve fitting. So you can use spline curve fit, exact curve fitting we want, exact for each. So how many samples will be there for your case? M niche data set has some 60,000 samples. So for every sample, you have to plot this plot. For every sample, you have to convert this discretized form into continuous form by curve fitting. That will be a spline curve fitting. Let's say it will be decided, but that should have the RSMA value, or let's say the R value to be, this RSMA value should be equal to 0, or this R value should be equal to 1. As in it should overfit. That's the whole point. So you can consider that as a continuous version of this. So I can understand that we don't have like the exact point. So whatever x0 and between x0 and x1, whatever values we have, we don't have that, like whether it will be the value that we have plotted the plot for. I can agree to that, but this is the next best version of that. So hope this point is clear. So you can assume other kind of function as well. So I can agree like that. So I'll just give an example of, so let's say these are your points. Let's say these are your sample points. You don't know the in-between points, right? The in-between points can be like this as well, can be like this as well. I can agree that can also happen. So it can lead to error. But what we are assuming is it's continuous like this. It's not having that kind of PV nature. So hope this point is clear. This will form your psi continuous in continuous variable format. Okay, fine. So hope this point is clear, which will be the function of your x. So whatever equation you get here, right, that will be the function of x, a single plot, as in a 2D function. So it's a single variable function, or the psi will be a single variable. This wave function will be a single variable function of x, right? This will be your first psi one. So what you can do is for all psis, you can find the continuous function, right? So hope this point is clear. Now moving on. So the second point here is whatever unitary will be having, whatever Hermitian matrix will be having, or Hamilton matrix will be having, whatever observer matrices will be having, like X, let's say V operator and P operator, or let's say any other operator, whatever will be having here, those are all in the form of continuous functions. Continuous functions. So fine. So what specifically the task will be here then? Like what value you are having, right? So what we are trying to do basically in quantum computing of this basically is you're applying a unitary to your input feature space as in input state psi, such that your output should be a target state, right? This should be a target state of that particular class. That is nothing but the whole problem of classification you're trying to solve. So this unitary, what you're trying to solve, should be a continuous function now. And what it should imply, how the unitary property will be preserved here, when you plot, right? When you plot this psi here, that should be in normalized form. What is the normalized form in continuous space? The probability amplitude as in integration, this area, whatever you will be having, right? The area under the curve, that should be integral from 0 to 1023 x, or you can say psi of this should be equal to, or this sorry, x. So this should be x, right? X dx, this should be equal to 1. So that is the sole criteria. Okay, so for making this unitary, whatever transformation you will be applying on this, that should preserve this criteria, that the area under the curve should be 1. So hope this point is clear, and these will be your probability amplitudes. So yeah, so this function is a continuous function. Now you have to train an ML model. So how to train an ML model, we'll come to that. Okay, well, that code is not given to you, you have to write it on your own. We can write it, but like that's that's your task. So like it's a simpler task, fairly simple task. We'll get into detail of how you can implement it. So unitary, we have discussed, it's a continuous function of psi, right? Sorry, it's not a continuous function of anything now, it's just a function. We don't know what exactly is a function of. What we have to do is use the unitary to map psi input, whatever you have, that is a continuous function of your x, your basis state x. Those are already continuous. So these psi are nothing but continuous functions of this, and you have to use your unitary to map it to continuous function of your target state. So if you know, like if you have been like present in the first lecture, we have discussed that the target vectors are at equal spacings, right? As in, if you consider just 0 to 63, 0 to 63 here is equal spacing of 7 7, right? 7 7 7 equal spacing. As in, if at 0 point, if it occurs, as in your probability amplitude is maximum after applying the unitary, that will belong to the class 0. If at 7th it occurs, it will belong to class 1, like that. So here how you can do that is, you have to preserve your area, right? So whatever function should be, whatever area you have to preserve, all the probability amplitude should have this integration in this interval to be 1. That will be your class 1. If it is second class, all the unitary transformations should be such that the probability amplitude, the probability density function, like after integration in this range itself, the area under the curve should give be 1. That will be unitary transform. This will be your unitary transformation 1. This will be your unitary transformation 2. Like that, you have to find all the unitary transformations for that classes. As in, how many number of classes are there? That many unitary transformations you have to find. U0, U1 up to U9. That many unitary transformations you have to find. Now, so how to infer? So hope this point is clear. Like so how to find this, we'll get back to, but hope this point is clear. Tavish?
Yes, it's clear.
Yeah.
So,
Yeah.
but in the real sample, we'll have 60,000 and not 63, right?
No. These are the feature spaces. Feature spaces. You are confusing the number of samples and the number of feature spaces. This is a single vector. A single vector as a single sample from the 60,000 points.
Okay, right.
Okay, and this we are considering as time independent. If you look into what you're saying, right? If you plot that point for a particular feature space, that would be a time dependent phenomena. Because in that, what you're assuming is like, if you, let's say you have image of 0, that image of 0 at t is equal to 0, if you're taking that, at t is equal to 1, you have second sample space. If you are assuming that as a discrete, like t is equal to 0, t is equal to 1, that t is equal to 1, that transformation, if you plot, that will be time dependent transformation. But right, we are not dealing with that. We are just dealing with
all the unitary operators 0, 1, U0, U1, and U up until U9 are basically just are normalized. That's what you said, right?
No, they are continuous functions. Yeah. So we'll get back to how to implement and how to find that. They are continuous functions for now. That's all you have to know. And visually you have known like what unitary transformation does. Basically, it converts from this. So it converts from this. So whatever like this is your plot, right? It converts from this to this plot. This plot. So let's say it belongs to class 0. It converts to this plot. That's it. 0 to 7. It converts to this plot such that this area under the curve should be 1. This area under the curve is already 1 for this case. If not, you have to make it 1 by dividing it by whatever value comes of that area. Okay, that you can do it.
Yes.
Yeah. Fine. So this unitary transformation is what you have to find for all the classes. So how you can train it, we'll get to that point. So now, since unitary U0 to unitary U9 are all continuous, right? Now one can argue that these are all linear functions, right? These are all linear functions, but that will not be the case here. This is an inspired approach. We are not taking that to be linear case. Since this is a continuous function, so it should have higher degrees. It should have higher degrees, right? So how to model any continuous functions? You can go to infinite series. We were probably limited to Taylor series at priorly, but now you can implement any kind of infinite series that you're aware about. If you're not, you can research about that. So there is Taylor series, there is Leibniz series, there is legendary series, Chebyshev series, many other series are there. And Taylor series is one of that. Burstein series also there. Burstein series it gives a better result than Taylor series. I'll share the resources for it as well. But this. So how to implement this? So let's consider we are curve fitting a Taylor series. Okay, fine. So hope this is clear. So you're taking this U0 to be for now is for in Taylor series terms is x0 plus this x0 different from what x0 we have, right? So let's say you want to implement. So let's say you have a function of x that is your u0 which you want to write in Taylor terms. So how to write it? We already know, right? A plus let's say a into x plus okay a square okay no okay just give me a sec. A0 plus a into x plus a into x square by 2 factorial plus a into so this a0 a1 a2 a3 x cube by 3 factorial, like this is clear. So there are 2-3 versions of Taylor series, right? So what you can do is, so what I have written is just about point x equal to 0. So this is basically what I written in Maclaurin series. What you can do is instead of taking about point 0, you can take it about point A. So that will be a more general model. So I'll write it on the next page. So basically what U0 will be having, you can model it into this terms. A0 plus A1 into x plus so we are taking it at about point this, right? Plus a2 into x minus a square by 2 factorial plus up to so on. So how many degrees you have to take? That will be up to you. Like we recommend at least going up to 5 degrees. For MNIST data set, even if you model it to 3 degrees, that is fine. But for MNIST data set, we'll recommend it to find for general any kind of degree set data set, what you will be modeling, right? Limit it to 5. And this forms as a general model. So what accuracy you'll be expecting here, right? It will be comparable to state of art. State of art, like whatever accuracy you'll be expecting here is above 97-98% in that range, because we have implemented similar cases. But this is a new implementation. So hope this point is clear. Now how to find this A0, how to find this A1, how to find this A2, how to find this A, we'll come back to X value. Will be what values, whatever vector values you have, right? That vector value will be putting here. So that vector value will be putting here basically. Fine. Whatever transition will be applying, right? Let's say you apply u0 on x. So all the values of x0 will be here, and you will be getting another vector that will be a transform form of this. Okay, fine. So hope this point is clear. Okay, so this will not be a vector now. So since we are in the continuous function domain, so it will be some function of x. That function of x will be here. That function, that Taylor series function of x will be here. Okay, fine. So hope this point is clear. Now how to model it, as in how to use ML pipeline for this. So basically there is one constraint that you have to impose, is that whatever function you will be getting after this unitary you're applying on psi, right? That integration from 0 to 63, whatever range is there, should be equal to 1. That will be your first constraint. What it does is basically it preserves the norm. So that will be your first constraint. The second constraint is that the range from 0 to 7, let's say it belongs to class 0. So range from 0 to 7 will be of psi of the target of the output of this, as in this only should be equal to 1. That's the second constraint. So this is the you can say bound limit of this. Bound limit of this only it is. So yeah, you can implement only one of the constraint. No need to implement both. And it implies what? The remaining whatever unitary of psi you will be getting, right? In the remaining spaces. From let's say integration from 7 to 14, that will be automatically 0. From 14 to 21, automatically 0. So hope that point is clear. Okay.
Yes, I got it.
Yeah, sure. So moving ahead, so this is your Schrodinger implementation. You have to implement it. So how to implement it again? Like these are the two constraints you have to implement. So this will be coming into a what combined loss function, right? And that loss function you have to backpropagate. As in that will be used for training what exactly here? That will be used for training your A0. That will be used for training your A1, A2, like so on, and this A as well. So hope this point is clear. And you can try implementing other infinite series as well with a limited set of degree. Okay, fine. So that will be your U0 to up to U9. And like you have to implement this and see. But like if it happens like let's say you're applying this, you have to infer this data. Now we are at inference. Let's say you have your state vector that you want to infer, as in which class does it belong to. You will apply all your unitaries, right? U0 to U9, and let's say the values overlap. It shouldn't overlap because unitary will exactly differ, like segregate. It's not linear unitary, it's a like higher order unitary, so it will exactly segregate. But it so happen like it, if it doesn't, then what you can do is introduce constraints of remaining things, like so you can hard constraint it more. So what you can do is integration from 7 to 14 is equal to 0. This integration also you can this integration also you can implement it in a combined loss to make it more you can say to avoid to increase the accuracy per se. Okay, fine. And there are like various other things. So what you can do is implement some regularization as well here. So like there will be, you will be facing many difficulties here. I can agree to that, because the higher the order you go up to, the initialization of this so happens like you'll get nan errors, and if like compute efficiency will also be lesser. But like you will implement it for 5, so that's fine. So hope this point is clear. For Schrodinger equation is clear. Heisenberg you already know. Moving on, Heisenberg we already given to you, right? So the second point is this, and now third, we'll be moving on to next formalism directly. So this similar thing is given here. So this thing, okay, right? Yeah. So yeah. So this thing, this slide gives the similar demonstration what we have been discussing. This slide is prepared by me itself. So what basically Heisenberg formulation does is applies a unitary matrix here, and then it transitions the probability amplitude, right? For this basically for amplitude encoding. But Schrodinger formalism, what it does basically, it has a continuous function that a continuous unitary is applied on that, and then you will get a continuous function. So that sigma u will be like changed, and that mu will also be changed. That mu will be having, right? That also will be changed. So hope this point is clear. Okay. Yeah. So instead of this Gaussian, you will be having some continuous function that you will be finding from curve fitting, right? So I think Schrodinger equation implementation itself, the racking of the brain, like you have to implement this and like trial and error will at least take 5-6 days, or like let's say 15 days. So apart from the Heisenberg like common task, what you will be doing, and this 15 days, so that will roughly take 1.5 months. What tenure you will be having, but like we will discuss more. So Britant, like what to do? Like we can discuss more formalisms as well, but like it will not possible in a standard to complete all this.
I think Britain left the meet.
Okay, sure. So that's fine then. Tavish, what we can do is continue. Like what we can do is continue, because like next quantum formalisms, it will be learning experience for you. So if you take that kind of interest, you can solve this problem in minimum duration of time, and you can move forward with the next task. And this is, yeah, this implementation, if like you will implement it properly, right, this will give a state of that accuracy. So hope this point is clear. Fine. Schrodinger formalism is clear. Then we'll move on to, so same thing is written here, quantum measurement, what we are doing with this probability amplitude. So yeah, okay, these two are the slides only. Yeah, continuous and this. Okay, so moving on, I'll explain from the slide itself. So these are the density matrix formalism slides. So what the slides basically are, so a density matrix formalism, if you are aware about Noel density matrix, what you have implemented there, right, in the code, that is similar to this. As in, first of all, a pure state can be written in this form, the outer product of psi with psi. a mixed state can be written in the summation of probability amplitudes of the outer products of the psi i's. So that's also written here. And the rho out, what you'll be getting is unitary transformation of that u rho in u dagger. That's also written here. So that's nothing but the forms of quantum computing, as in just to give this. So yeah. So basically, what we are doing here is you are having a novel density matrix here, novel density matrix, and that density matrix for a single, instead of a vector, you are having here a density matrix. How to get that density matrix from a classical data set is this. There are various other ways, like we have discussed on your first meet. So that can be done here, and then you're applying unitary transformation. So here unitary transformation, how you're applying, because it's a Hermitian matrix and because your diagonal elements, it's a Hermitian as in the upper and the lower elements are same. So you have to apply your unitary transformation 2 times, and a second thing is a matrix. So basically how to do is rho in u dagger. So you have to apply this unitary transformation 2 times, because this is nothing but a Hermitian conjugate of this, if you're about the Hermitian property. So this should be there applied here. So this will give a route, and that is nothing but the quantum computing done here. So you can try this, but since the novel density matrix is included in your common task, no need to do this. Moving ahead. So this is your Wigner formulation. So what exactly is a Wigner formulation? We'll go into details of. Basically, you have an analog image, it is converted into digital image, then it is flattened. Then what you're doing is normalizing that. Okay, up till this point is clear. So what we'll be getting here is amplitudes, right? Probability amplitudes. Then you'll be getting your density matrix from outer products of the vectors. So this point is also clear. So so there are so how to get your Wigner function. So if you look into the last point, what is written here, your Wigner function is equal to Hadamard of that S, right? So what that S is nothing but a spin vector. So we are not going into details of the physics. We're just dealing with the mathematics here, and it's oriented to an application point of view. So this equation is what you have to implement. So Wigner function is equal to HD dagger S. So how to get that HD? So that Hadamard transformation is done here. So this is one of the quantum nets that can give your Hadamard matrices. There are others available as well. So you can go through that. So this, what it basically does is, whatever your size is of your, let's say, density matrix, right? So this density matrix, after flattening the density matrix, whatever your size is of the density matrix, 16, let's say for this case is 4 cross 4. So if you flatten that, that will be 16. The Hadamard gate should be of that many dimension, 16 cross 16. Okay. And for amplitude encoding, you can scale it to similar level. Like if it is 63, if it is 1024, like how to scale it, you can get an inference from here. So this scaling, this Hadamard gate, you do tensor product that many times, you'll get your Hadamard gate. Then so you'll have to apply your Stokes vector or a spin vectors to this. So what exactly the Stokes vector or a spin vector here? So this what it is written here, right? This forms this is very small in handwriting, but I hope this is clear. So S00, XX0, SY0, SZ0, S0X, like that up to SZ will form your vector, right? Those vector is what you have to find. So how to find that vectors per se here? Those are spin vectors. Those are nothing but your this equation 0.25 into trace of rho. What rho you gotten from here, right? So what rho you gotten from here, that rho is nothing but this. And for first case, S00, S00, and then S0x. So this is a cyclic sequence what you are following, like what is followed in a Stokes vector. So this S00, SX0, SY0, this you can infer for higher dimensional data. So that higher dimensional inference is also given in notes. You can follow that doc file as well. So that higher dimensional inference, like how to get it for 1024 vector or let's say 63 vector, you can get an idea from the document shared with you. So this using this equation, you already have a density matrix. You can tensor product the I cross I and then get the subsequent values. So this what x0 means, basically you have to tensor product x with I and then multiply that with the density matrix to take a trace of that. So this will form your spin vector. You already have a Hadamard gate. Multiply that, you will get the Wigner transformation of your classical data set. Once you have a Wigner transformation, what you can do is you will get basically a vector. That vector will essentially be non-normalized, and it can have negative probabilities as well, because that's the property of Wigner function. And then similar quantum computing picture comes into the picture. So what you would apply is a super evolution operator here. Super evolution operator basically means whenever the density matrix, or let's say a matrix, is flattened in the form of vector, the operator what you'll be applying is called a super evolution operator. So that name is just that thing. You can apply non-unitary evolution as well here, and then what you'll be getting is like evolved version of the Wigner. And what this Wigner evolved version we want, basically want it to be our target set. So if you're aware about the Hermitian target states we have to discuss in density matrices, right, per class, that that per class discussion we can imply here. And in for equal spacings, you can put one there, right? For equal spacing one, so it will be similar to your one hot label encoding, equal spacing one. So you can go there and check in the density matrix code, right? Fine. So moving on, Smith decomposition. Smith decomposition basically tells us about whether the given state is entangled or not. So what you can do is let's say. So we have been discussing Heisenberg quantum matrix formation. You don't have to implement that; it's already implemented. Schrodinger, you have to implement that and take that as your like primary task. Density matrix formation, no need to implement; it has already been implemented by us. Wigner formation, we are discussing detail. Implement that. Smith decomposition and Everest. Everest we have implemented. You have to make, you have to take the tasks like written there and implement that. Okay, fine. Then this Schmidt decomposition is one of the decompositions. After that, like these are all the task, or this first and second condition also we have discussed in a note. This remaining task, whatever are written here, right? That what you do is, if time permits, you have to write a report on that. So specifically for the application of classification, you don't need to go into like too much depth of theory, like and the history of this. No need to do that. Just to get the basics right to medium depth, then implement it for classification algorithm. That's it. That's all you have to do. So because like you'll have many papers for each formalisms, you'll have like many papers throughout the history. You don't need to go into that much depth. You don't have that much amount of time as well. Basically, we want this report for application point of view. That's it. I hope this point is clear. Now, two formalisms are remaining that we'll discuss. So this is Smith decomposition. So what exactly is Smith decomposition? Convert this into your digital matrix. Then you will flatten that. You normalize that. The same similar density matrix you will be getting. So this what you are discussing, right? You have to implement that for every vector. What you have, right? For every vector. So if your compute power is that much, is fine. If it's not, then you have to like the n value you have to reduce. N value to reduce to let's say 8,8. After flattening, it will be 64. That you can implement for 50,000, 64, because that 64 cross 64 will be your primary matrix for Wigner. 64 cross 64 flattened 4096 will be your Hadamard. 4096 or 4096. That will be for every like matrix, every data set. So you have to reduce the size. You can take 4 cross 4 as well, for just for a demonstration purpose, if you don't have that kind of compute power, because the data set size will be like 50,000, like not 50,000. So yeah, 4096, 50,000, 4096, or 60,000, 4096. So and the matrices will be like that of that length. Okay, fine. Yeah. So this you are aware about, right? This. So how to do this? We have superunitary evolution operators. The target states we have discussed, right? The similar implementation, what you have been implemented for Heisenberg implementation, similar implementation you have to do here. Okay. Now coming to the this density matrix we have discussed. So what you can do is reduce the density matrix to a specific. So you can form a we can convert this into two bipartite systems. So this is one of the like you can say first system, and this is the second system, rho A and rho B, and those are like found from these equations. Trace of B of rho A B. So how to like trace out the B and get your system A. So if you're not aware about this operation, you can have a look around and you can go into details of this. But this has been implemented here. You can directly get an idea from this implementation as well. Get the eigenvectors, eigenvalues of that. Get the eigenvectors, eigenvalues from that, and then like this state, whatever input state is there, right? So I'm at the leftmost corner here, Smith decomposition. Whatever leftmost state is here, so you can write that in terms of this form. As in, if you are considering just your A like decomposition as in reduced form, then you can write this: the square root of the eigenvalue of A. This square root of 0.7294 is nothing but your eigenvalue of your A. Square root of that, and these are nothing but the eigenvector vectors. So this is nothing but the eigenvector of A, tensor protected with the eigenvector of B, first eigenvectors, plus the second eigenvalue square root of that, and then the subsequent eigenvectors is multiplied. And you can do the similar thing for B, and you'll find that both the results are same. So hopefully that point is clear. this the last implementation. So you can implement this. So what this basically will give you an idea. So this will not help you in classification. So it can help you in classification if you apply that level of post processing. So what this will give you the idea about is basically is the state or is the like matrix when flattened on when quantum amplitude encoded, whether it's entangled or not, to like it's entangled or not. So how to get the inference from here? The number of positive eigenvalues will give the inference, like whether the state is entangled or not. So we'll just get that inference. We don't know how much level of entanglement is there, but we'll just get that inference. So that's all you can do here. By implementing, you will not get. But from that inference is what you can do is apply the algorithms of reduction, let's say PCA. So because that relates to correlations of what data set will be like how data set is correlated. So based on the eigenvalues, what we'll be getting for like every vector, you can form that which vector to keep, which vector to like neglect. So that kind of, if you'll have that kind of algorithm knowledge of MLs, and you can correlated that or implement that here, then you can form certain kind of algorithm that this can be used as a pre-processing too. But for now, you can keep it as just as implement this and then decompose the state, and you can say that this many states are entangled in our given data set and these many states are not. That's it. Fine. And you can apply other kind of evaluation metrics as well, to get the whether the state, how much level of entanglement with the state is, whether it's a AME, absolutely maximally entangled state or not. Okay, fine. Now second thing is last implementation is Everett. So Everett has two implementations. Both are implemented in your code, so you can go through that. It's a fairly simple implementation. What Everett basically tells us is, whatever state we are measuring, right, that measurement state will have certain loss of information. As in, let's say we have four quantum states. We are measuring that state. So what you will be getting after output, you will be getting a single state. You will not be getting the three remaining states, right? So these three remaining states, where it will go? It will go to the second universe. That's what the average implementation or thought process was. It will go, or it will propagate to the second universe. It will not so happen that the information will get discarded there. So that is what is implemented here. If the measurement result is 0, this is your state. So since this input state is symmetric state, so whatever, if the measurement result is 0, if the measurement result is 1, that states are also symmetric, but in actual data set those are not be symmetric, those will be different. And if you look in the document, we have given the case specific for it. If they are different, then how the for both implementation it will be like so hope this point is clear. So if the measurement result, let's say you are measuring the fourth qubit, so this is having 4 qubit states. Let's say you are measuring the fourth qubit, as in the last qubit. If the measurement result is 0 in that, what will be your state? If the measurement result is 1 in that, what will be your state? So you know to write it there, right, in this linear algebra form. If the measurement result is 0 of the last state, whatever states have the last 0 present in that, only that state will remain, and you have to discard that state. So the first state will remain, the second state will not be there, the third state will remain like that, the fourth state will not be there, fifth state will remain like that. Like that additions will are written here. And if the measurement result is 1 of the last qubit, then only the second state, then the fourth state, like fifth state, sixth state will be remaining. Like these are written here. If the measurement result is 0, measurement result is 1, then you have to perform your normalization. Normalization, as in, it automatically happens in quantum computing circuit. When you measure a particular thing, it gets automatically normalized as per the Copenhagen interpretation, whatever implementation you are doing on actual quantum hardware. But here you have to normalize, because this is an inspired approach. You're not actually measuring, you're taking that physical phenomena and then putting it into the mathematics format as a discrete level here. There are many arguments whether it's a continuous measurement or we are not getting details of that. We are just taking it as a discrete measurement. What it does, we already know. Okay, fine. Then we are applying normalization of that. This is a normal state, this is a normal state, and again, as we discussed, this is symmetric, so this will be a symmetric state itself. Then we are measuring third qubit measurement on both. Then it will again have two separations of 0 and 1. So what Everett basically told us that if the measurement result is 0 of the last qubit, then that will be universe 1. If the measurement result is 1 in the second qubit, that will be your universe 2. Like that's what's the implication we have implemented here. So hope the thought process is clear. And this similar thing is done, and up till last point it is done. So the last state, so this many universes will be having, and this is nothing but the last state. So what you can do, this post processing is important. We have tried 3-4 approaches of the post processing. What we have done is, after getting this state, we have concatenated all the states what we have gotten, normalized that, and then tried to infer using a neural network architecture like whether it gives the accuracy or not on the trained neural network. So it doesn't give. So why it doesn't give? It's not pretty the probability distribution itself is changed here of the underlying data. So that's why the neural network cannot assume, or we have to use more complex neural network. We are not like gone into that details. But what this basically does is you can say changes the data set completely. So you can go into details of what exactly the normalization, what it does to the data, what measurement does to the data. That's important here. So those are the two things that changes the probability distribution of the data itself, and hence the training accuracy and the test accuracy are not to that much like scale. Hope this point is clear. And there are like many other ways. What you can do is like if your target state is like 1 at the top, this probability should be 1 and remaining all should be 0, right? But since we are normalizing that, remaining also probabilities will propagate here. But ideally that should have been case. So why doesn't it happen? That also point you can research. Otherwise the implementations are all done. Whatever tasks are written there, kindly go through that. Fine. This is just one of the implementations. Second implementation, you can do dog. Uh, yeah, so this is the doc we have shared with you, right? So yeah, so this doc has a Schrodinger beginner, then this mid decomposition average. So average, we have been discussing this first point, right? The second point what we are trying to discuss here is like what average thought. Another thing is that it's also called as Henry's you can say universe splitting. So this was a state vector splitting, now it's a universe splitting specifically. So what average thought is specifically, each universe will have different set of governing laws. So to implement that different set of governing laws, what you have done is you have added a unitary. So for every different universe or every state vector splitting, you are applying a separate universe that will be defined whatever unitary you are applying, that unitary matrix. So that is done here. The same thing, only what you are applying is you're applying as unitary matrix on the subsequent level. So this what normalization layer is, right? After normalization, you're applying a unitary. That's the only thing in the state vector splitting difference and the universe vector splitting. So hope this is universe splitting. Hope this point is fine. Now, like these are all the discussions done with you. These are all the implementations which we are not done. What we will do is research all this. So we have implemented the fifth point, we have implemented the fourth point, we have not shared the code with you, but like there are many implementations that we have not done. So like what you have to do is research to the level that it can be applied to the classification algorithm. So you have gone through our research, right? This is what our research is. We have in-depth knowledge about all this formalisms, and that is what we can apply it for classification approach. So this is also a first and second quantization is also discussed here. You can have a go through. It's a fairly simple to understand. It's nothing there. We have taken the Hamiltonian. This is nothing but the Hamiltonian transformation. Then the Hamiltonian can be written in terms of kinetic energy and the potential energy setting. And this you already know the equations for x in terms of x cap and p cap. It's nothing but p cap square upon 2m and plus half into m into v square. Plus half into k into x square. So let's say spring mass oscillator or in that setting. So or you can say LC oscillator. So x and p cap, what will be getting? It should have the constant of your uncertainty relation. So that constant should be implied here as in x cap p cap minus p cap x cap should be equal to I h cross. So that uncertainty Heisenberg relation should also be implemented here. And what you're trying to do basically here is you're trying to quantize your data. So whatever Hamiltonian you have, right, that Hamiltonian you're trying to write it in terms of first and second quantization terms. So you can go through these details. It has been given here, right? And if you have any queries, you can ask us in the chat Slack section. So fine. And these are all the points like you have to go through. So I find them like Feynman path integral, classical and local like hidden variable theories. So this Wigner theory, what we discussed, right? That the alternative name for that is nothing but Bohm interpretation. So that is also been discussed here. And you can go through the von Neumann equation and entropy, rho log of rho summation of that. So you can go through the details of that. Okay, fine. How to implement it for classification algorithm if the time permits. Your primary task is implementation of Schrodinger algorithm. So what we discussed, Schrodinger formalism for classification approach. Fine. Okay. And this since this session is recorded, if you found something as I can say heavy to graphs, you can go through the discussion again, and you can go through docs. I'll share the PPT as well, only the relevant sections with you. You can go through that as well. Now let's move on to the code. We have 10-15 minutes remaining. Could you please kindly share your screen, Tavish, and open the codes?
Yes, I'll do so. Wait a second. Uh, I'll just run it on Jupyter Notebook. Give me 2 minutes.
Sure, take your time, no issues.
Yes.
Because the code shared with you, I think is only like Everest is total implementation. Heisenberg already shared with you, and the remaining what is shared with you is the demo implementation. What we discussed on this thing, right? These slides and slides. What you're discussing the slide. That's the same implementation what we are shared with you. So you have to implement that, scale it to the classification approach.
Right.
Yeah. We'll move forward with the first one. The second one is fairly like simple too. Yeah. So you can think of, so one point we missed in discussion, average neural network, what you can think of is applying a normalization and a measurement as an activation function alternative to the activation functions what we're applying in your conventional neural network. So hope that point is clear. And here it is splitting happening because a ReLU function is discontinuous at x equal to 0, and that is usual activation function. That splitting, like it can be related to that splitting as well here. But like ideally it should have been the case, like it should have been exactly classifying it to the target states, but that is not the case. So what you can do is you can if there is certain loss of information like involved, what you can do is instead of taking unitary, you can go take a non-unitary as well. So like yeah, so that's just a statement I want to do it. We can discuss in terms of code as well. So this all Wigner, Smith, and other encodings demo. So this what we have done is specifically taken a random vector. That array is written here. Normalize that. That is nothing but an amplitude encoding. So what task basically for you is this amplitude encoding is implemented. You can type for phase encoding, you can type for binary encoding, you can type for angle encoding, and you can also type for like a unitary encoding. Dual density matrix encoding you can try, but that's a different formalism itself. So you can try it here itself. No issues. Fine. Okay, so moving on. So this is your density matrix, what you are taken, np.outer I, comma a. This is fairly simple and easy to understand the code, right? So this I is nothing but identity matrix. What you discuss, we have to first create. So first is nothing but the Wigner implementation. So we have to create all your poly x, poly y, poly z matrices. So that is why these are nothing but the poly x, poly y, poly z matrices created here. Same, and that's a reshape to 2, 2. So hope this one is clear. So could you please go below? So this is nothing but the first is nothing but spin vector or Stokes vector calculation. So this Stokes vector calculation which we already discussed, S00 x0 for specifically for this case is nothing but S00 x0. But what we have shared the document with you, it gets the inference from this itself how to scale it for larger vector. So this is nothing but a Stokes vector. That Stokes vector is we have gotten here. Then you're taking a Hadamard gate. You know your Hadamard gate. What is the 2x2 elements in that, and then you're Kronecker productivity in 4 times because we already discussed the dimensions for it, and you're multiplying that with your Stokes vector. So this Wigner, if you go below, this is your discrete Hadamard transform. We go below. This is your Wigner. So Wigner np dot conjugate discrete Hadamard transform dot transpose at the rate x. What it does is basically give you a Wigner vector. Now if you look into this, this will have. If you look into this, let's calculate the norm of this. The norm of this will be like not equal to 1. Like you can find this. And second thing is this are nothing but should be your probabilities, right? These will be your probabilities. So these probabilities are negative here. You can check. So this negative values. So that point is also like we are trying to make. And so could you please go above? Like yeah. So here what is missed? Here only your Wigner transformation is done on the classical data set. What we have missed is we don't have a target vector, right? So that is why we didn't find the unitary. You have to find that unitary. What you have to do first is for every classical data set or every data point, you have to find this Wigner transformation. Once that Wigner vector you have gotten, as in higher dimensional space, for every like data point, you can use the similar code what was shared with you for using the SVD approach, using the quadratic decomposition approach, or using the ML approach to find that unitary matrix or that non-unitary matrix of that evolution, super operator evolution. and the target states will be what? Target states will append equal spacing target states. So one hot label encoding is analogous to that target states. So hope that point is clear. Yeah, and then moving on, this is your second implementation. This is nothing but Smith decomposition implementation. So this rho A, rho B values are nothing but the like reduced density matrices. We have taken that to be random for now, and those are reshaped. We have taken the eigenvalues, eigenvectors of that, and then the Smith number we have calculated. So this for I in the eigenvalues. So whatever eigenvalues we have gotten, if the I is greater than A, like we have appended that to the A, or like so append 1 or like we have appended that as a 0. So we are just focused on the sign of the eigenvalues because it plays a crucial role in identifying whether the given state is entangled or not. So yeah, fine. The similar thing is like given below itself. Like you can go through the code, and this is printed like whether the state, but depending on the Smith number, whether the state is entangled or not is printed. So both state, whatever we consider, are entangled based on the Smith number what we got. So that point is done. Yeah. This is what implementation. Go to go below. Yeah. Yeah. Below. Yeah. And just write down. Yeah. Okay. Yeah. Just this, right? Okay. Yes, the similar thing is done. Okay, I think the similar thing is done. What we like, what is tried here basically? Yes, yeah, I understood the thought process. What was tried there? Means at that day, like I was trying basically to go into spaces that are not like if you go into 2x4 sections or 4x2 like different you can say density matrices sizes, then what will be the effect on the Smith decomposition? That was I was trying to find. That implementation also done, but this you can you can ignore for now because your data set already is you can say separable as in two matrices itself. So you can ignore that. But yeah, you can go through if you need it. Fine. So it's written here, non-square wave does not work, right? This try tomorrow. That was a thought process implemented on that day. But anyways, so this point is clear. These implementations are clear. We have discussed Wigner. We have discussed Smith decomposition here. We have not discussed like code for Schrodinger is not implemented. So, but we have discussed in detail how to implement that, how to incorporate machine learning in that, how to incorporate Taylor series or infinite series in that. Okay, remaining like first and second condition also not implemented. You can go through the code doc shared with you for that. And whatever is remaining, like if the doc is shared with you, kindly implement that for the classification approach. That's it, right? So primary task will be your Schrodinger implementation and then this implementations. And if the time permits, the remaining like whatever like points are written there, like every approach you can write it for classification. Fine. Could you please kindly open the second code, Everest code?
Yes, I'll do so.
Yeah, so these is specifically written here, right? Everything what we discussed or like lesser than that is discussed here. Like you can go through. So this was thought out like exclusively for this project itself. Everything like can be implemented here or whatever point we discussed that can you can also like try to add in this task. So go through this. Yeah, and now this is nothing but what we discussed on the first day as well, is the preprocessing of the data set. We are separating the class labels and the images as per the classes. So this is done. You're taking that array of that. This has been like discussed before itself. Yeah. Yeah, so you're separating as per the class digit 0, digit 1, digit 2 like that, and then you're resizing it. So basically you're resizing here as in, so for average implementation, if we look into the code below, like the splitting happens, right? The splitting code itself like takes a lot of time to juggle around. So you'll be getting, so since it's implemented, it's easier for you. But if you're taken 1024, right, that implementation would have taken like, I don't know, 2-3 days to implement. That didn't just go through the indexing itself. So because the sheer size of that splitting is very high. For every data set point, you have to do the split. So it's very high. So anyways, yeah. So this what we basically so yeah, trying a different set. So yeah, so this code was shared with you. Okay, fine. You can so what this is tried. Go above. Can you go above? So what is tried here is instead of taking the equal spacing target vectors, right? What we have tried is taking states, target states. Those are maximally separated, but those are like not equally spaced. So those are orthonormal, maximally separated, and different from what we are like you've been using one hot label encoding. So this like we have tried whether it increases the accuracy or not. It doesn't. So you can try implementing other target state vectors as well here. Fine. Yeah, you can go through the code. It's simple and fairly easy to understand. So this is nothing but the Gram-Schmidt decomposition of the vectors that has been done to maximally separate that, and then orthonormality is verified in that, and yeah, so on. Could you please go in the code below? This is not a relevant code for you, but yeah. A different set of target vectors are typed. So you can see the target vectors is given that repeated vectors. So yeah, so input state vectors like you converted that and reshaped into arrays. So this is the second set of target vectors. What is commented out here? You can try like uncommitting and implement that itself instead of repeated vectors. But since this approach was like, you can think this approach was taken from the fundamental itself, I was hoping like it will give the state of the art accuracy, but it didn't. So like I was trying a different approach as well for different target states, but it still didn't work out. So first task like this, go through the code, then try like getting the inference why the accuracy is not comparable to the state of that, like where the, so you have to go into details of measurement, go into details of normalization, because those two are the activation functions that are used here. So go into details of that, and yeah, so this this like code has already been explained in the first like discussion itself. So this is the implementation of orthonormal matrix code. These are the loss functions like gram zero matrix identity zero orthonormal loss. These are all the loss functions, and yeah, so this is multiplied with your input vector to get your output vectors here. Output state 10 vectors is written here, is appended to that that output matrix, unitary matrix what you got from training into the input vectors, and this is done for similarly for the test vectors. Now this is no, so this is not for the test vectors. Now we are just going through the first loop, as in whatever vectors you have are of the size 50,000, 64. Now what you have to do is index, as in what indexing you have to do. The first half, as in the even indexing, if you're measuring, so how we can write this state basically, this 64 state, as in 64 basis, how we can write is basically 0, 0, 0, 0 up to 64. First basis state, second basis state will be 0, 0, 1, the 64th element or the 63rd element if you're starting from 0 will be 1. Like that you can write all the basis state, right? Those basis states will be the basis states here. So that basis states are what are indexed here, as in if you look into this, even numbers are taken when the measurement is 0, and this odd numbers of that indexing are taken as when the element measurement is 1. So hope that point is clear. Now after indexing, the second step, the activation function comes into picture here. That is normalization. That is done in the second step. The normal output state vector 32, 0 and the 32 underscore 1. Then yeah, so these are nothing but normalized. These are initiated to zeros first, and then it is printed. That's the shape is printed just to check it if it is coherent or not. So like first I tried implementing it for 5 and 2. So like it was kind of tedious task. Later resolved it to 64, as in reduced it to 64, just for reducing the code blocks, number of code blocks. You will find that the number of code blocks here are like very much, because you have to index it again and again, the same thing. Now it index for 16, and that 16 indexing you have to index it 4 times. Like that you have to increase it up to the point like last will be 1. So can you go kindly go below? Yeah, so similar thing now, like this model, what this model basically is, the second model what we discussed of the Everest implementation, the unitary, imagine the multi-universe model, because you're applying unitary again in that case, and then like similar thing. So hope that point is clear, because the similar thing is done here. So whatever states you're getting normalizing that, then you're applying unitary, right? So same thing is done here. Yeah, this is the same code, the above code itself, but the linear whatever dimensions are changed here in the code, and the output and input vectors are changed. Remaining code exactly remains the same, and the the remaining states as well. Like this is done for the 2, as in 0 and 1, both measurements separately. So yeah, okay, fine. Okay, yeah, similar code. Then could you kindly go below? This is your first unitary by ML method. So what you can do is remove the constraints of unitary here from the ML model and try incorporating it non-unitary here instead of unitary. That can also be done to get that system, or to get an open kind of system instead of closed system. So there will be a loss along with the normalization and the measurement used as activation function. So whether that loss incorporation can act as a universal approximator, that we have to implement and see. So yeah, This is fine. So similar thing is done here. So if you understood the explanation here, the similar thing is like, so this vectors are multiplied with the unitary what you got and to get your output vectors of 32 correspond. For your state 0, if the state 0, major state of the fourth qubit, or in this case, if the major state of the sixth qubit is 0, then your first implementation. If the major state of the sixth qubit is 1, then your second implementation. So yeah, and this again is indexed. So whatever state you have right now, for you add just the 0 and 1. Now you're indexing it again to get your 16 0 0. If the result is 0, then what? Priorly the result is 0. Then after that, if the result is 0, then this will be the state. Priorly if the result is 0, now if the result is 1, what will be your state? So this is the state, like that. The indexing is done. You can go through the indexing and how it can be like, you can write it on the piece of paper and you can infer for small data sets. Similar inference you can apply here. So similar indexing, it scales up. If you write it in the scale of like what you have written, right? That similar indexing you can scale it to 6 qubits, 7 qubits. The indexing part I'm saying, as in why we have taken this indexing 1 to 2, like this indexing starting from 1 and the equal spacing of 2. Why we've taken that indexing for all the samples for this case, so that you can infer from writing a small state. Fine. Similar thing is done below itself. So there are two implementations. What you can try is, first is removing the unitary itself in between unitaries itself and try seeing the result. Second thing is like apply the unitary, then see the result. Apply the non-unitary, then see the result. Then research on the unitary activation functions like measurement and normalization as the activation function, and whether incorporation you can say increase the accuracy or not. And the last thing what you're going to do is post processing. Whatever post processing we are done, like apart from that, are there any other post processing that you can do to increase the accuracy? Now in this case as well, if you look into, if you applied subsequent unitaries, or if you're forming that as a multi-universe case, then in that case the target vectors are also like what kind of target sector vectors can be implemented for the small systems or that reduced systems after measurement. So that target states we have kept it as a coherent, but that needs to be changed as well. So what that change should be, that you can also research that. So there are many points to research here. So that's why keep the Schrodinger equation as your primary task, Everest as your primary task, the report as your third task, and whatever tasks are written there you can go through. Apart from that, the remaining implementations are not that much important. Like you can try implement it if the time permits, but this is the primary task for you. The task given there, Schrodinger, this task, Everest. Okay, fine. And if you go into below, there are like inferences done. So how we are getting the inference for the taste data, that is done below. Yeah. Could you kindly go below, Tavish? As in, yeah. Yeah, at the last, as in after the like, single indexing remains, right? After that, there is so this code we have explained. No need to be afraid of the code. It's like the same code. So this implementation of post processing, that also you can try to research. So like there are various implementations that start here. After that concatenation was tried, you can try researching that. So yeah. So hope this is clear. If you have any queries you can ask us, like yeah, and the time.
Yeah, I think I understand what the task is and all the order of how I should approach all the tasks.
Okay, fine, cool. Tavish,
Should I
then
stop sharing my screen?
yeah, sure, and like you can leave the meeting as well. Okay.
Okay, thank you. If I have any doubts, I'll text you on Slack, right?
Sure, yeah, sure.
Okay, works, cool. Because I think I'll have a lot of doubts while going through all these tasks.
Sure. You can go through the code. You can go through the discussion again. Still, if you have any queries, like this is little bit of fast discussion because we had a time constraint. That's why, and we can arrange a separate session as well for that. If you have any queries like that, yeah, sure.
Okay, works. Thank you so much.
Thank you.
Good night.
Yeah. Okay. So hi Tulsi. We'll move forward with your. So I think you're also busy with your own task, right? So we'll try to keep the session of discussion scripts to 1 hour, limited to 1 hour. So yeah, without any further ado, we'll discuss first the docs that are shared with you. Okay.
Before that, can you do me a favor?
Yeah, sure, please.
The AI that you're using, I think it's sending the transcript to my college email, and my organization doesn't give like admin access to these. So can you like share it with my personal email so that I can read the transcript?
Okay, sure. But I don't know your personal email. So whatever email you have in your CV, right? That is the email which we have. So if you can
Okay.
currently, like, if you can send us a text us on Slack your email, like we can send you the transcript as well, as in the total email what you get after this.
Okay. Yeah, that's better.
Yeah, sure. So yeah, moving on. Um, Yeah, so this is what, so we have specifically, since these both algorithms are very short, like we have given you two tasks per se. One is quantum initial algorithms for the application of classification, and second is a different architecture that we came up of on our own for specifically for that case of application. But there are like still nuances that needs to be figured out. It had been implemented, but the accuracy is still subpar. So why it is subpar, and you have to research on that. So we'll discuss in detail what. We'll discuss this first. Okay, so
Okay.
this is nothing but so this algorithm is there around. So as in people have been researching about quantum algorithm from the start itself. So this algorithm is a similar implementation of that. We have applied it to the classification approach. That application point of view, this is an old approach, but this algorithm has been around for. As in what this algorithm basically does is, if you apply a unitary, what it wants is, if you are having for let's say for first k qubits, you are having the state. So ignore this quantum encoded. If you're having the state as x state, so what this unitary or what unitary want to apply, it should have the first state to be x, and then whatever state was present on the ancillary qubits, that state should be XORed with a function of xm. So that implementation of that algorithm has been around. So that we have coined the term for that as quantum initial algorithms. So this has been specifically like applied for classification. So hope this point is clear. Like, we'll go into details of what exactly each code block and how implementation is done. We'll go through the code as well. So basically what we are
Are
done
you
here is,
sharing your screen? Because I can't see any screen.
oh, sorry. So like Tavish shared his screen, right? So I thought my screen is already shared.
No, it's okay. Okay, I can see it
So
now.
yeah. So what we discussed for now is this quantum initial algorithms have been around for let's say 2 or 3 decades. So this is specifically we have fine tuned it for the case of application. So what we have done specifically here is, we'll go into details of that. This input state, what you are having at the start, is nothing but a input qubit ground state. So that input qubit ground states are nothing but how many qubits you are having. In the zero basis, you can write in terms of number of zeros. That means number of zeros. So what this basically in terms of vector format will be, your first index element will be 1 and the remaining all will be zeros. That is fine. Now this quantum encoded classical data section, you have to implement it particularly on quantum computer. You don't have to implement it here because we are already, so let's say you take amplitude encoding, you already have your classical data set, you already are converting it to matrix, you're already factoring it, you're converting that into normalized form. That is nothing but amplitude encoding. So you're already having your access to that normalized amplitude encoding. So you don't need to implement this unitary block for like encoding. So this block essentially is nothing but, we are not taken that as unitary. This is nothing but encoded classical data. That's what is important. So after this, so let's say your classical data after quantum encoding, it's limited to let's say first k qubit. So on that first k qubit, your state will be this, right? This k x state.
I'm
So and the
sorry
remaining,
again.
yeah.
Your doc is sharing. So if you're writing something, I can't see it. I
No.
can
So
see
this
the
doc
doc
itself,
that you have shared.
I'm explaining from the doc itself. So you want it writing
Okay,
format?
okay.
I can
So
explain
you're
you in
not
writing
writing
format.
anything on it. Okay.
Yeah, actually, like I had a session yesterday as well. So since I'm sharing from tab, I don't have the cursor pointing here, so I can
Okay,
understand it will
okay.
be a little difficult to understand. But yeah, what we can do is move on to this scribbling kind of setting. Fine.
Yeah.
Okay.
I just
Yeah.
didn't know if you
So,
were like writing something or not. I'm
okay.
good now.
Cool. So this is nothing but your quantum encoded classical data. So excuse my handwriting, but
Yeah.
yeah. Okay, quantum encoded classical data, right? So this state what you are referring to is as XM. Okay, now
Yeah.
whatever ancilla state, so this is fine. What we are doing here is applying. So you did not need to apply your unitary because you already have access to it, and we are in inspired domain. So again, fine. Now what you're doing is applying a unitary here. That unitary, if you're aware about from the first lecture discussion, like first discussion, that unitary can be found by SVD approach, that unitary can be found by ML approach to certain speciation scale, that unitary can be found by QR approach, or that unitary can be found by like you can physically train a neural network circuit or a quantum neural network circuit in which U3 parameterization circuit or a C0 parameterization circuit or RX, RY, RZ parameterization can be trained by backpropagation. But we're not dealing that here. We are just limiting to SVD, ML, QR. So SVD implementation, ML implementation, QR implementation already shared with you. Kindly go through that. Now this, after this, so we are fine tuning this algorithm which is already present. So what this algorithm basically does is it applies a unitary transformation such that this transformation after these applications will be XM only here. Here it will be XM only, but it will transform this. So let's say, so your ancilla qubits, so how they are decided physically for our classification approach. If you look into your MNIST data set, they have 10 classes. 10 classes as in, so if you're to encode these 10 classes into one hot label encoding as in the target vectors, what you can do is the minimum quantum in quantum setting is scales up to as 2 raised to n, right? So minimum vector you can go up to is 16. You can go below that as well, as in you can go for 4 as well, but then equal spacing cannot be applied. So you cannot apply one hot analogs to one hot label encoding here. So that's why you're using 4 ancilla qubits here. So in which case, let's say you have your first state at this. So your initialized state is this, ground state is this, right? Now what we want specifically, so what this will be, you can ignore this, but the second state what we'll be having, right? This state you can take this as label 0 of your class. You can take this as label 1 of your class. So you can take the remaining things as label 2 and label 3 with sufficient amount of spacing. Again, here there is no equal spacing possible, as in it will be spacing of 2 sometimes, 1 spacing sometimes. For equal spacing, I think you have to go up to 32. But like for that again you have to increase 1 qubit. You can try that as well. So that will be like equal implementation, as in if it increases the accuracy, it works with us. But for trial you can start this and try this, and this has been implemented as well. So what this basically does is this unitary applies this transformation. So whatever transformation, these are nothing but your 4 qubits. It applies a transformation of this setting. Whatever input state you have, it will XOR this state with your XM. That's what it does. And that's what the algorithm also implies, this unitary. So how to find this unitary per se? You have your input vectors, right? As in,
Yeah.
you have your input classical data set, all the vectors here, right? What you can do is, for every vector, you can Kronecker product this state. As in this state in vector format. This state in vector format will be your 1, 0, 0, 0 up to 16 cross 1. 16 cross 1, because this is 4 qubit state, so it scales up to 2 raised to 4, 16 cross 1. So you can tensor product your this state with your classical encoded data here, and you can get your input state. As in, you will get your input state in the form, I'll write it in next page. So you'll get your input state for MNIST data sets basically in the form of let's say you are taking your so you're limited your MNIST data set to a 64, as in after amplitude encoding your setting is this. So you'll be getting you have to Kronecker product this. So you'll have to add the number of qubits, how many there are. So you are taking 4 ancilla qubits, so that will be a 2 raised to 10 state, as in this will be your 1024 2 raised to 10, yeah, 1024 60,000 comma 1024 state, the input state, this state, right?
Okay.
Yeah, so this state will be your 60,000 comma 10. So hope that point is clear.
Yes.
Yeah, now you have your target states, right? But you already know what this algorithm implies is this should be your XM itself. So whatever you have taken this, right? Taken this, like taken in the start, that similar state should be here, right?
Like control bits. Kind of.
So similar state, as in the control bits, whatever you'll be doing is on this, as in whatever states, or you can say whatever XOR operation on this function will be doing it on this state. This
Okay.
state should
Got
remain the
it.
same. Yeah,
Got
this
it.
state should change as per the classes.
Okay,
So
makes
yeah,
sense.
so if you can think in terms of that, so I can understand what you're trying to say. So this is what you're trying to imply. So but for here, that kind of thought process is okay, fine, that you can also imply that kind of thought process. So let's say if it is x, if it is 0 here, what you can do is I can agree to that. Like if it is 0 here on the target, if it is 1, then you can say that this will be changed to 1. So that is fine on the controls section. That is what we are trying to do here is, but this unitary is black box, as in that is in matrix stage. So for transferring that, you'll have to use discrete transfer function, and after that you'll have to check the circuit, like what the circuit is, and whether this operation per se will be like not be limited to this. There will be many gates in that, so you cannot exactly infer that whether this will be the case. Just a simple gate or a simple XOR operation, whether it's happening using just a CNOT gate. So that is why like we have kept the discussion for a unitary like matrix of 2 raised to n cross 2 raised to n. Fine.
Okay.
Now this, yeah, this is nothing but an XM. So let's discuss on next page itself. So output state will be of this form now. Tensor protected with, let's say your this state belong to a particular class. Let's say kth class. K varies from 0 to 9. If this belongs to your kth class, then depending on what class it belongs to, you will have to append that encoded state here. That should be your output state. So hope this point is clear. As in, let's say your class is 0. Class is 0, then we have discussed previously, right? This should be your state. This should be your state. If you have provided that state as to be class 0.
Okay.
Yeah. If your class is 1, then you can take this as this state. If your class is 2, then you can take this as this state, like that. Up till 9
Hmm.
class, let's say you are taking this as 1 1 1. This. So some 1 and 2 spacing will be there, because this is of structure of 16, like 16 states are there and you're just having 10 classes. So there will be spacing of just 1 or 2. So it's not equal spacing case, but you'll have to like write this as in keep a note of what classes you append to which state. After that only you can infer here, as in we have segregated our classes, right? You have data of 60,000. What we have done in our code specifically for class 0, we have segregated the first 6,000. Let's say roughly it is 6,000 number. Second 6,000 we are segregated. Then the last 6,000 we are segregated. As in like this setting, we have segregated all as per the particular class. So if it is out of this 6,000, if this vector is out of this 6,000, what the state should be? The state should be 0 0 0 1 for this case. This will be your total target state for the training the unitary. Hope this point is clear. If it belongs to second class, this state should be your 0 0 0 1 0, like that. Whatever state you applied, right, that state should be here. So that will form your target states. If you look into our code which I shared with you, the
Yeah.
start code, in that start code we have itself defined the target states, because this what we're defining, right, this we have defined there itself, because in that case we have used different algorithm, as in we have used unitary on all the data set and we have not appended some kind of ancilla qubits. In that case,
Mm.
what we're trying to do is whatever like vectors we have, on that itself we are trying to get the information from. So let's say this has 64 vectors, 64 features. So that features itself are nothing but a number of qubits, and those number of qubits are limited to, and this itself forms our target states. But here we are trying to infer from here, right, as in the last four qubits we are trying to infer from that. So that is why like we are putting our 1 hot label, analogous 1 hot label encoding here, and then Honecker protecting this with the output state what we want, as in this is the output state. Then you already know like unitary, how to train your unitary. You can train your unitary based on the code given to you. It can be SVD approach, it can be ML approach, it can be QR approach. You can train your unitary. So what parameters like you have in your hand? So this unitary is not in your hand. Even if you increase the number of parameters, right, that will be unitary itself. It's not going to help you. So what parameters you have in your hand is increasing the number of ancilla qubits. Try thinking of other modifications that can be done to the architecture, like that can result in increase in accuracy. So once you have trained your unitary, so this was our circuit. It's totally disabled now. Okay, so basically this was your circuit. So let's say this. This was your circuit, right? And we have your output state. Now, like, but what you want from here is that there comes a next challenge here. What you want from here is are just this four state, right? Just this four state, but you are in quantum inspired approach. So you cannot exactly like get the inference from measurement. Actually, what you have to do is measure the states, and then after the measurement, like you can get a clear cut picture whether it is 000 or whether it is 001 depending on the particular class. Like let's say if it is 00, ideally if it is 0010, then what should be the case? Because why it will be 0010? Because you appended that this to be the case, right?
Yes.
You appended so means XOR this with your function of XM, and that function of XM should be your target state. That is what the algorithm is designed on. This function of XM, because this will apply some transformation on your feature space such that it will map to our desired target states, and that will be the particular class. That is what the thought process for the algorithm was for classification approach. Okay, fine. So and since you're like XORing this with this, output will be whatever target states you have. This target states will be same as in this target states, whatever you have 0010, 00011, like that. That target states will be here. That after measurement, the probability amplitude for that should be high enough compared to the other 15 possibilities if you measure in Z basis or Z basis, and this should be a output state for that particular class. So hope that point is clear. But what happens is now how to implement that, like in the code we'll go through, but how to implement that, as in for now the code has been implemented such that this output vectors, like you're training your unitary based on this output vectors and input vectors, right? But you don't have your measurement criteria. So how to incorporate measurement on a classical system? So that is the second point of research. So we can do indexing setting. So how to do that indexing? Basically, how many number of feature vectors are there? Let's say you have your 60,000 cross 1024 output vectors, right? What you can do is reshape here, just reshape to what? 64 comma the number here, as in what 16, 64 comma 16. That's it. That's all you have to do. So what will this imply basically? So not this case, 16 comma 64 is what you can do. 16 comma 64. Yeah, so what this will basically do is this 16 will imply the particular class, as in let's say 001 is there. So what is the class there? You will have to this is the second position of this, if you're getting the point. The first position, the zeroth position, 16 means what? You'll start from 0, right? 1 2 like that up to 15. The first position will be your 000. We are not assigned any class to that, so the ideally the probability for that should be 0, right? It will not have any probability based on the algorithm itself. The second case, the second position of this 64 should have your as in this position, right? You can write that in binary basis. Yeah, this is the position, and this will be a corresponding XM. So hope you are getting the point what we are trying to do. Are you getting the point? As in what we're trying to do basically here is segregate as per the class. If 000 is there, there will be no corresponding this 64 what you have written, right? There will be no corresponding state, as in the probability amplitude for that will be very less of occurrence of that state for every sample. So what this basically does is let's take a single sample, right? Single sample, as in you have 60,000 right here. Now you're taking just a single sample from here. Now, what the single sample will have basically from our circuit will have each class's probabilities appended to it, as in a tensor protected to it, if you're getting the point. So, as in the state can be written in this format, right? 000, if let's say your vector belongs to class 0. So, your XM belongs to class 0. Plus, at second position, this this second position. So not this, sorry. So this x0 should have been here. So I'll write it on the next page. It will be clearer to you because the ancillary qubits are below, right? So xm tensor protected with 0 plus xm of class 0 tensor protected with 0 plus up to so on xm of class 0 tensor protected with your 1 right? Now what we are trying to imply is basically the probability amplitude associated with this should be very less because you are not assigned a particular class to that. So hope this point is clear. This will
Yes.
have a class 0, so this should have a maximum probability of occurring. This, the as in the probability amplitudes, whether it be here or whether you can write all the probability amplitudes outside. So the probability amplitude of state of occurring should be nearly equal to 1 and the remaining should be 0. That should be ideally should be the case. So that is what the thought process for implementing this algorithm is. So hope that point is clear.
Yeah.
Yeah, and if it belongs to class 1, if it belongs to class 1, then the corresponding, so there will be one class, then this all probabilities should be 0 and the subsequent 0 state, the state associated with that should have a maximum probability of occurring. Hope that point is clear. Now coming to the main point, here we implemented amplitude encoding, right? But if you look into the crown jewels, growers, shores all uses binary kind of encoding setting. The numbers, decimal numbers are encoded into binary format. So what you can try first thing, apart from the implementation given to you in amplitude encoding setting, you can try binary encoding there. That's the first task, and whatever subsequent tasks are there, those are already given to you or written in the code. We'll go through that as well. This completes your first architecture discussion. So hope this is clear.
Mm.
Yeah. So moving on to your second discussion. Okay. So you can go through what's written here. The similar what we discussed, right? The similar thing is written here. If you have gone through
Yeah.
after this discussion,
Yeah,
will
I
be
went through this.
yeah. So if you have any doubts in that, you can ask later or now in yeah. Yeah, different architectures of QML classification. So yeah, so this is a second architecture what we came up with. It's a similar architecture as in, but it's like you can say a different architecture. What we have in hands in quantum algorithms are basically different architectures. So that's the case in neural network as well, right? So what we are trying here is basically like this target states, what we are putting there at the ends, right? What these target states, now we are trying to reduce the systems, we are trying to measure the two systems at the 2 qubits at the end, at the start, then later 2 qubits, and then gating only the 4 qubits, and that 4 qubits should have our required class as target state. That's what the whole implementation here is. So like first what you have done, so you're able to see the screen, right?
Yes.
Yeah. So this quantum encoding is what you've done. Let's say you have taken amplitude encoding. You have your feature vector space to be 64 plus 1. So you have taken your amplitude encoding to be of say a section 64 plus 1. So it will have 6 qubits here. So your top qubit you have measured, you have measured your last qubit. You will be remaining directly with your 4 qubits. That 4 qubits, first you can apply your parameterizable unitary on that, and then like then you can so this measurement will not be the case there because now it's limited to just 6 qubits, so you don't need to incorporate the parameterizable unitary 3 here. Just parameterizable unitary 2 is fine. And then after that, like after application of that, this should be the states, as in whatever classes you like assigned to that particular target states, that should be your output states. Ideally the probability amplitude for that should be 1. So that was a thought process for incorporating this. So here also you can try increasing the size of the input space. So what exactly is a parameterizable unitary here? If you look into for implementation of QNN, if you look into parallel library as well, so they have used RX, RY, RZ parameterization and a CNOT gate. So those or what they're parameterizing by using a backpropagation algorithm made with parameter shift rule or any kind of backpropagation algorithm specifically designed for quantum algorithms. But here what we're trying to do, this is quantum mismatch approach. We are tightly using TOT library. What we're trying to do is basically defining a function make unitary. After defining a parameterizable like size, we are defining a function make unitary. That make unitary takes the random initializations into a space of unitary, and then we are trying to train that unitary such that, so we are trying to train this to unitary such that this output unitary should be your specific target state. So how we are doing that? That's the simpler case, simpler, not simpler, because why you have to again reshape here, right, in between. So
Yeah.
again you'll so that reshaping will what it will do, it will increase the size of the data. So you can think in terms of 2-3 ways here. So that can be one of your data augmentations, as in whatever vectors you have, right, after let's say you are measuring, what measurement basically means is like we are reshaping it, that's it. Reshaping is means what, let's say yeah, I'll write it, it will be better for you to understand. Yeah, so what we're trying to do basically is, let's say 6. Okay, this is your parameterizable unit, right? After this, now what you're trying to do is measure this, right? Measure this. Now you'll get your 4 qubits, right? That 4 qubits, what you're trying to do is apply a parameterizable unitary again, then you'll get your 4 states. And ideally, what should be the case here? This should be your target states, what you're training your 2 unitaries for. So how to train this? As in, the main task here is, you can make this unitary, you can make this unitary, not an issue. The main task here is how to perform this measurement in your quantum, in your classical setting, using torch library itself. So what you can do is, you can reshape this, whatever like thing we did in your previous algorithm, right? You can do the similar implementation here. As in, what you can do is reshape this such that your middle thing means, as in middle 4 qubits should be here, and the remaining 2 qubits should be the setting. But if you implement this, the problem for implementation of this, what it will be, what the torch library, or what the tensor, like you can say this means is basically there are 2x1 vectors which are having 16 in one dimension and two values in that dimension. So this 16 values, what we are having, right, that 16 values should be here actually, because then we'll have the exact grasp of the vectors, as in it will be in that setting what we require. So those 16 vectors are what you can do is 2 comma 2 comma 16. That is what you can do, and change the indexing size instead of taking this. So what this implies basically is, this 2 is for your this qubit, this 2 is for your this qubit, and this 16 is basically for your this. So what this basically means is, if your measurement is 0 in your first qubit, this qubit, if your measurement is 0, and in your second qubit, if your measurement is 0, that will essentially imply the positions of 0 0 in this, the positions of 0 and 0 here, and the corresponding state to that will be your that state, which will be state obtained after measuring this as 0 0 here. Now if you consider 0 1, so what will be 0 1, as in this will be 0 in that case and this will be 1 in that case, if you're getting the point. And the corresponding state for that will be your that state when this subsequent measurements of these 2 qubits are 0 and 1, and then subsequent 1 0 and then 1 1, like that 16 state. So here, I hope this is clear. Once this point is clear, you will be having here 2 comma 2 comma 16, as in you will be having basically your let's say 60 okay 4 you'll be having your 4 comma 16 sheet, as in you'll be for each vector value what you will be passing, you will be having 4 vectors produced after this, 4 vector produced. So hope this point is clear.
Okay.
Yeah, so this essentially is forming a data augmentation in reduced space, data augmentation in reduced space, in reduced target space. With augmentation is what you are increasing the size of the data, but since you're applying your parameterizable unitary, so this will be in your target space, not in your input space, because since you're applying a unitary, right, this input Hilbert space will not be changed to your target space. So like this can have application in QGAN, as in how it can be in QGAN application, the whatever subsequent states you'll be getting, right, the 3 remaining states or all the 4 states, that all 4 states, what you can do is apply a UU dagger on that, apply a UU dagger on that, and you will get a new state here. So that can be a thought process for getting a new data set point into that probability distribution space of your input vectors for that particular class. But that's a like far away thing. For now, we're just a classification, we're limited to classification. So moving on. So this thing is clear. Now we are applying again a parameterizable unitary such that we'll be getting your output state here as 0 0 0 0 0 0 1. If you assign this state as the output state for that class, fine. This is all your implementation, and this is what you implemented in Tout library itself. So now could you please kindly share your screen
Yeah,
with the code? With the code, yeah.
yeah. My laptop's Wi-Fi drivers are fucked up, so I'll just like share it from my iPad, if that's okay.
If you can open your code, that's also fine.
Yeah, if I join it to my laptop, it's gonna uh kick me out
Yeah.
like 100 times. So I'm just gonna
Yeah,
share like
that's cool. Like, does
thing.
your iPad have that kind of like ID for opening the code? If that
I have
you have
PDF
that,
file
that's
of
fine.
that code.
Oh, that's cool then. Yeah.
Yeah. Let me how do I share screen? Okay, I don't know how to share screen.
Okay.
Let me see. Okay. I
Okay.
don't
There
have
is an
option to share screen.
okay. Let's see.
Okay, found it.
This
The br-
option is there. Yeah. This stop sharing option, like for me, like I can stop sharing this.
okay. It doesn't like me. It says your browser can't share your screen. That is funny.
Okay.
Let me just join from my laptop then. Hopefully
Okay.
it won't kick me out of the meeting.
No, like if you'll keep this meeting on, right, it will directly switch to a laptop meeting.
Hmm.
Yeah. To see, is it? Are you able to open the screen on your laptop? Or otherwise, I can try connect it from my laptop. That's also.
It's loading. It takes my laptop. The Wi-Fi drivers, they're really bad. So the Wi-Fi keeps turning off and behaving on my laptop.
Okay. Okay. Just give me a sec. I'll try connecting from my laptop. Oh yeah. So you have said.
Can you see it?
Yeah. Yeah. Sure. Yeah.
Perfect.
Yeah. So these comments like have been thought out specifically for your task. Like, could you kindly go through the comments, like not now, but when you read the code particularly, and then try incorporating whatever like we have discussed in your session session as well. And this task, these are your tasks, like main tasks. Apart from what we discussed, right? So this first code block you will go into. This code block essentially what we discussed is separate classes and separate images. That is what is done here. Basically, the defined section is there, right? We have first used the IDX2 NumPy library, couple converting it in NumPy array as in digital setting, and then this separate images and labels are basically we have separated each images to particular classes because we are following a sequence here, and we are trying to you can say maintain the balance of the number of classes. So yeah, fine. And then please go down like this. We have plotted that, and if you are aware about the first section, we have discussed this code at length and the first discussion session, so no need to go over that. Basically what this code basically does is it converts your input image into a digital matrix, and then it flattens that, and then it normalizes that amplitude encoding is at the bottom. Like, yeah, this is nothing but the plot of the image after resizing and before resizing. There are two plots done there. Yeah. So we have appended each yeah, so this what you have done, right? This input state vector 0, we have converted the appended list into array, and for this case implementation, we have limited our data set just to 500. So for easy implementation, because the size of our, like as we have discussed in our case, it was 1024. So for avoiding that, so we have kept the size of the input image to 64 itself, and that this data set size also we have reduced. So it will affect the accuracy for MNIST data set specifically. It will affect the accuracy just by 2-3%, but not that much. Like we have tried implementing it for reduced data set as well. So MNIST data set is carefully crafted data set. So whatever maybe the size may be limited, but the you can say the architecture is able to clearly identify the underlying probability distribution, and hence able to clearly classify irrespective of the size of the data set, and the you can say classification accuracy is I can say decreasing by a small amount, even if it decreases the data set size, reducing a small amount. So this you have taken all your input vectors, appended it to a like list, and you have converted that to an array and then reshaped it. That is what is done here. Now comes your main implementation. So this remind me again, this is the initial, right? So this is the first algorithm what we discussed, right? Yeah, yeah. Reshape and appending all the things, right? So like that. Yeah. So this so forgive me for not commenting here specifically. Like this was done in quite a bit of haste. I like we know like apart from you, like there are like you can say many you can say interns that we have been planning this like doing this coding for, and doing the doc file as well. So segregating that and doing all the things. So yeah, it took quite a amount of it, but hope this is still clear. We have tried to be as you can say crisp as possible and to the point as possible in the code, and it is easily understandable, readable code. So what we have done basically here is input ancilla, which we already discussed. We have taken that as 4 to be the in number. So we have initiated that np.zeros to be 16 in this case, and that 2 raised to 4 comma 1, that is nothing but 16. So that forms, and then we already know that the input cubic down state is of the form of 0 0 0 0. That is what we have taken at the state, and then in vector format we have taken that first index of that to be 1. That is what is done here. The similar now we have to form your input data set, right? As in input state product state, what we discuss as in input product state, what it will be, the 60,000 for our case it will be 5,000 comma 64 examples what we have, that needs to be tensor protected or connector protected with this what state we have here, input ancilla. So that our tensor production np.crom of n comma ancilla is done here, right? Upon that is nothing but amplitude encoded here. So hope that is fine. So this code what is written here, right? np.crom of m comma ancilla upon np.lng of non of np.crom of this original state bank. So this is nothing but amplitude encoding for dimension of, you can say 5,000 comma 1024. See. Okay. Okay. Now that had, yeah, just a sec. There's a okay, fine. Yeah. Okay. Yeah. So okay. Could you please kindly share your screen again? Yeah. So yeah, we are not here, right? This is a different implementation. Heidelberg individual task. So we are at initial. We were at initial. So Tulsi, are you there?
Oh, yeah, we're here. I'm playing with one button.
Yeah. Please kindly like you have stopped sharing your screen.
Yes, yes, I'm here.
So you have opened your
Oh,
Steam
did
tab.
I?
Yeah.
Let me try
Yeah.
again.
Yeah.
Okay, I'll start again. It's
No. So no. So you were sharing your screen. Blunder from my side. You're sharing, but you're sharing a Steam screen. As in you change the, you can say, display tab. Yeah.
okay.
So now you're sharing your Steam screen. So yeah.
Okay.
So there is an option of entire screen like sharing. So yeah, your
Is it
screen
good
is
now?
visible, but you have shared your window screen. You have to share your entire screen for changing the tab. Or you can share a window screen as well, specifically that particular Jupyter notebook section where you show this PDF.
Okay. Oh, I have shared my entire screen. Can you see like the
Yeah. Could you please kindly minimize
forward?
this then? Minimize this browser, or at least change this tab.
Wait, the Wi-Fi driver acting up because I was in the coding tab
Okay, then what we can do,
all this
Tulsi, is
time.
like what you can do is like tomorrow, if you are
Okay,
free, then
so sorry.
yeah, no issue, no issue. So what we can do is tomorrow we can have a 15-20 minute session with on the scripts. Like if you're free at let's say 9:15 to 9:30 or 9 in that range, we can arrange a quick session discussing this code. It's just a 15-20 minute discussion. It will not take that much long. So yeah, that is also fine. Cool. Hi, Tulsi. Yeah.